Okay, well, let's get started. And so as I promised last time, what we're going to do initially is we're going to talk a little bit about configuring I2C. Now, just to kind of give you a sense of how this is used, I just happened this morning to receive something on communication using I2C, and basically the approach or the interface is used to tie a number of integrated circuits together. So I'm just going to flash over here briefly so that you can see that. Let me see if I can move this over. So I have this link here, so you might want to look at it, though it's not necessary that you go through it, but it just kind of helps motivate the topic that we're talking about, because I2C is something that is used in a number of applications, and so that's why I want to expose you to things that might be beneficial to you after you leave this course. So let me minimize this, and let's come back to our discussion. So as we saw in our previous discussion, when we communicate using I2C, and I'm going to have to bounce around a little bit to get to this. There's no easy way to So we see that we have a fairly complicated protocol when we communicate with I2C. And so I'm going to walk through this, but I'm going to use some different slides that will be a little bit closer view, and this will help put the software configuration and operation in perspective. So let me come back to this presentation here, and let me change my view here. So in this communication sequence, we have the situation of multiple devices are all asserting signals on this data line. The top trace here is the clock. The clock, again, is generated by the master, and the bottom trace is basically all of the slaves and the master asserting signals on this line, and we talked about it previously when we looked at the wired OR configuration. So just to refresh your memory, I'll bounce back here a second. So let me come back to our previous lecture. We saw that we have all of these devices tied in parallel, and we have a open drain configuration of where all of the outputs and all the inputs are all tied to the single line, as shown on here. And so this is a synchronous half duplex communication. So that means that only one station transmits at any given time and everybody else is receiving. So if we come back over here, what we want to do is we want to be able to communicate. And so we see, just to review, we have a idle condition where both signals are high. The start condition is basically indicated by the master bringing the data line low while the clock is high. That signals all of the receivers that data are to follow. Now, because when the master first starts communicating, it has to indicate to whom the address is going to go. So in this case, we have an address, and I have my device with an address, a 7-bit address of 10F or 101111. So it'd be in hexadecimal 4F. So we see we have 1 0 0 1 2 3 4, and then we have one additional bit to indicate whether we're going to read or write. So this says, okay, I'm going to write. And at this point, the master has finished transmitting, and now the slave has to acknowledge that it has received the signal. So now the slave asserts, it turns on the transistor to basically pull this signal low to indicate that it has acknowledged that it has received the signal. So now the master responds by keeping the signal low, and now it is going to, the slave keeps the signal low because it's going to respond with data. So going to my next slide, if we look at this part here, now the slave is basically changing these data lines while the master is changing the clock. So we see 1, 2, 3, 4, 5, 6, 7, 8 data lines. And now the slave basically turns off its output transistor. The pull-up resistor pulls the data line high, and now the master is going to bring the data line low, saying that it acknowledges it has received that byte of data. Then we have another set of 8. 1, 2, 3, 4, 5, 6, 7, 8. This is the slave now sending 8 bits of 0, and now it releases the data line, and now the master, instead of pulling it back down to say it has acknowledged, it does a negative acknowledge because this is going to be the end of the transmission. So moving it over to the left a little bit, this is the data. The slave has released the data line. The master does not pull it down. It sends a negative acknowledgement saying, okay, that is the end of the message. At which point now the master brings the data line low. It raises the clock from low to high, and then so when this transition from low to high is done while the data line is low, that indicates the stop condition. So you see that there's a little bit of a complication in the interaction. And I mention this because when we look at the software, we're going to see that there are a number of function calls that we need to allow us to be able to do this synchronization. Okay, so let's come back to our configuration of our system. So we look at our data sheet, and we look at the MX7, and we see that we have 5 I2C interfaces or I2C interfaces, and we can use 4 of them, and after a little bit of assessment, we decide that we're going to use I2C1. So then we see, all right, I2C1 is available on the MX7 board, and I showed you those connectors on top. Okay, so now we say, all right, we need to configure the software. And so we go to the SFRs, and we have to decide what is it that we're going to configure. So we look at the SFRs, and we see what are they actually for. And so as you see here, these are the SFRs. So we have our configuration or control. So this is the I2C, and because we have 5 of them, these refer to the individual I2C. So that's what the X designates. And if we look at the SFR table, we'll see we have the numbers 1 through 5. So we're just interested in the last part, the control. We have a status, a baud rate generator. We have the register to where we're going to, if we're going to send data out, we're going to transmit data, we write to that buffer. And if we're receiving data, we read from the receive register. And if we are a slave mode, because recall our device can operate as a master or a slave, then we have to configure our own address, and we can also, if necessary, respond to multiple addresses. And so what we do is we use this mask to say which bits are we going to ignore. So we'll respond to multiple addresses. And when we configure it, we can also configure it for interrupts. And so just like the UARTs and the SPI, we have a number of interrupt modes that we can potentially use. Okay, so let's look at our SFRs. And let me come to the table over here. Well, before we do that, we also let's decide what we're going to communicate with. Okay, so we're going to communicate with this temperature module, and this is also capable of using 7-bit addresses, so that's going to basically govern how we're going to communicate with it. And we see that we have the signal lines that we are interested in, but what I want you to focus on is on our address. So we have some jumpers on this little device that we're going to configure with our addresses, and the address that we're going to use is hexadecimal 4F. It's a 7-bit address, so we have 3 bits in the upper, for the upper significant character, the 4, and we have 4 for the lower, so that's where we get the 4F. And by putting the jumpers in the appropriate position from the center to the 3-volt side, so it's a 3-array jumper, and we see that I can either put it from here to 3 volts or from here to ground, and so that's how we'll configure the addresses. Now notice we have, in our I2C, we have 7 address bits, so that gives us up to 127 possibilities but we only have 8 possible addresses using this little temperature module. So this is going to restrict which addresses we can use out of the entire address space. So if we're using other devices, we need to make sure that they have the ability to use addresses other than the ones we need here. Okay, so now we say, all right, we want to start looking at the code, and we want to configure our device. And probably the easiest way to do this would be, let's look at our peripheral library. And what we want to do is we want to, I'll find the open. We have our open, and notice our library only indicates open I2C1, open I2C2. And I'm not certain whether or not that this can actually support all 5. It may be able to. I haven't run that experiment because these other I2C interfaces are not quite as convenient. Okay, so let's look at our SFRs that we have. First and foremost, we have to turn the I2C interface on. We may choose to use it in the idle mode. If we are in the slave mode, we could use this release control bit, not necessary for our master mode. And similarly, if we're using I2C, so I2C reserved address, we can enable or disable that. 10 address bits, we do not need that. We'll use 7 bits. Our slew rate control bit is, we either can enable that or disable that. We have our input level bits, so SM bus, and we're not using that. So then we also have our general call enabled. This is for slave mode, so this would be something for like a broadcast. A clock stretch, again, that's a slave mode. Acknowledge bit, this is something that we would need for master mode. And then acknowledge enable, we also need that for master mode. Our receive enable, also necessary for master mode. Our repeated start condition enable bit, necessary for master mode. And we also have 2 other, for restart condition enable for master mode and start condition enable for master mode. Okay, so those are, I skipped over. I must have skipped one, but in any event, so those are what we need to configure. So let's look at a software option of where we're going to use that. And I'm going to use it in a very, very basic mode. So in this case, I'm using all the default configurations, and I'm just opening it by enabling it and setting the baud rate generator. Okay? And I have to say, send my slave address, which I've configured as 4F. And so first thing I'm going to do is I'm going to send a string of data. So I have this buffer that I'm going to use, and let's see where I have that defined. I don't, oh, here it is. No, well, I have it defined. I think I have it defined in my, oh yeah, here it is. It's a global variable. Okay, so I'm sorry for the jumping around. Okay, so I'm using the first 2 addresses. There will be instances of where I potentially want to send more data, so that's why I have a data buffer of 4 bytes. And so in this case, what I do is I do the slave address, I shift it left 1 position as I indicated before, I set the least significant bit to 0, indicating I'm going to write. And then the data that I have is 0, so what I'm doing is I'm writing a command to the temperature module. Okay, now if I look at the temperature module, and I showed you that it was very, very lacking in terms of information, in terms of what does this device do and so on. So we have this temperature sensor integrated circuit, TCN75AVUA, and so what I have done is I've basically gone to the data sheet, and so this is the temperature sensor that's used, and I want to come back over here to, so it has a number of different operational modes. And so what I want to do is I want to use it in the mode where I'm going to read the data, the ambient temperature register, which is register 0, so I'm commanding it to read the register. I can also set temperature limits and so on, so I can generate alarms, but I'm not interested in that for our applications. So what I'm doing is I'm basically configuring this so that I can measure the temperature, the ambient temperature directly. So coming back to the code, what I've done is I say, okay, I'm going to command this device. I'm writing to it, and by writing this 00, I'm selecting register 0 for that module to read the data. Then what I do is I have 2 bytes to transmit, so I start the I2C. I send the start bit, and I'm waiting for it to complete. Now, I'm going to interrupt here for a second. So we're going to see that we have a number of modules, and that's where this comes into play. So we have some functions that you'll see in the code examples I'm going to use. The first one is this start, and this start I2C basically generates the start signal that we saw in the protocol. I also have the stop, which generates the stop at the very end. I have a restart, which will, as you see, reads a restart. What I want to draw your attention to is this idle. So I'm waiting for a start condition, a stop condition, because I may be a slave or I might be in the master. In the master, I want to make sure I have an acknowledge bit. I might want to get a receive indication, and so I also have my acknowledge functions. Now, one of the things we'll find is these acknowledge functions and not acknowledge functions can also be done, or they'll be incorporated in some of the other functions that we use. So for example, when I do this function here where I say, okay, I'm going to start and I'm going to wait for it to be idle, and what I'm going to do now is I'm going to do this master write. And this master write is going to ultimately do some of the operations for me. And so what I do is I send 1 byte, I wait for that to complete, and then I wait for acknowledgement from the slave. And if I get the slave acknowledgement, then I do the next byte. And so once that's done, then I generate the stop, which recall is the negative acknowledgement, and then I do the idle. So actually the negative acknowledgement for the message is going to be done by this master write, because I have basically gotten the acknowledgement from the slave, and then I will do the stop condition, which will be the negative acknowledgement, and the wait for that to complete as well. So when I want to read data, so again, I restart the bus. So this is if the bus is not stopped, then I will stop it, I wait for that to be idle, and then I start that process all over again. And so I do a write. In this case, I'm doing the slave address, and I say, okay, I'm going to read. And now I'm going to read temperature. And I know this is a 2-byte sequence, so I'm going to read 2 characters. So I specify 2 because I know the message is going to be 2. I have my pointer to where I want the data to go, and then I have a timer indication with this 152. And so I read those, and then I have to, considering the format that the data is transmitted, I have to now basically mash it into one single integer. And so what I do is I take those two characters that I have received, and then I basically OR the most significant with the lower significant. So I OR them together because those are 8 bits. I OR the 2 into a 16-bit term, and then I now shift it back to put it in the proper format. And then I indicate a delay so I'm not reading it so fast. And so part of this is just massaging the data to put it in the proper form. So I look at a little bit more complicated example, and so in this case what I'm doing is I'm using the LCD display. In the LCD display, we've gone through all of the configuration of that before, so I'm not going to go through that again. But what I do is I now configure my SPI as before. I clear the buffer, I set my baud rate generator, and then what I do is I clear the overflow in case there is an overflow. And here's my config. Oh, this is SPI. I'm interested in I2C. So my I2C, again, I just use a very basic configuration, and I go through the same process. The only thing that's different in this case is now I go through my initialization, and then I'm in a continuous loop here of where now I'm going to continually read that. So here's the slave address. This is a read command, and now what I do is I say, okay, I'm going to read those two values just as before, but now what I'm going to do is I'm going to convert it to degrees Fahrenheit. So what I have this raw temperature, I convert it to degrees C, and then I convert that to degrees F. And so I use my standard conversion formula, and again, these are integers. I could display it, I could use it in the floating point format as well, but I'm just doing it as integers. And now I take that integer value, I convert it to ASCII characters using this sprintf. So I'm printing the character to a string, and then I use that string to write to the LCD display. And so I have this operational, and let's see if I can okay, so I'm going to try an experiment. Hopefully I can do this without damaging all the components. So you see here on this display, well, let me turn it right side up. Might be easier to see. So you see that I have a display that is indicating -77 degrees. And as I put my fingers on this temperature sensor, you see that hopefully I'm not at room temperature. So now I'm basically causing the temperature on this integrated circuit to increase. And then as I remove my finger, then I see that temperature decreases back again. Now, this is a handy device where we can actually communicate using the I2C, and we can do a lot of different things with this interface using the I2C. But the important thing that I want to convey to you, and we'll go through it more in the labs, is that the complexity of the protocol is introduced because we are using a very simple electrical connection. And so in the lab videos, I'll go through in a little more detail of how we design our interface and some of the characteristics of how all this works together. So let's see, there's a question, the to and master get, see, okay, so a question about this function here. Okay, so when I say I'm going to read from the I2C, I'm going to read 2 characters or 2 bytes. So that 2 indicates how many bytes I expect in the message. This is the array that it goes into, and then I have my timer configuration. So when in doubt, we can go to the peripheral library, and that was get let me do it this way. If I can find the function. Oh, here it is. Okay, master get SI2C. Okay, so we see the parameters. We have our length, we have our buffer, And then this is a data weight parameter. So this is a timeout count that we would use. And so again, where I got good examples of the timeout count was from some of the examples like this code example given right here. So this what happens is we have to know a priori the size of the messages. So what happens is if I come back to this indication here, in fact, let me go to the other one, which is, so in this case, and this is actually reading from the temperature sensor, this first batch of clocks is the master commanding the slave to send it information. Okay, now, because I know that the device is going to send me 2 bytes for the temperature, recall I went to this table over here and I say that, okay, when I do ambient temperature, I'm going to send you 16 bits, which will be 2 characters or 2 bytes. And so when I do this command, I know it's going to be 2 bytes. So when I say get master get I2C, it's saying get me 2 bytes, and once I receive the 2 bytes, now me, the master, I'm going to generate this negative acknowledgement saying that is the end of the message. And then I will generate a stop bit saying that is the last of the transmission. And then if there's any other transmissions, we start all over again using this protocol here. So it's kind of a intricate. I can't just say send me data. I need to know precisely how much data because the master needs to indicate, and this is the master now generating the negative acknowledgement saying, okay, that's the end of what I expect. So it's not as straightforward as maybe some other communication protocols that we might use. Okay, so coming back to my OneNote. Okay, so any other questions on I2C? Okay, so what I'm going to do is I'm going to reconfigure my hardware here for a second. So I'm going to pause the recording. Or I'm going to try and pause the recording. Okay, where's the recording? Okay, we're back. All right, so what we want to do now is I want to just do a kind of a brief review of things that we have talked about. And of course, given the fact that you can review all of your material during the quiz, kind of changes the dynamic of how this is all done. But what I want to do is just kind of review where we've been so far. So recall we've looked a lot about computer. So, and in this case, I think I can now come back to my. So we've looked at stored program computers. And we looked at characteristics, various architecture characteristics. And we looked at a lot of the details of the RISC processor, particularly the MIPS processor, which we use. And we looked at all of the various sorts of instructions and so on. But what is important is one of the things that is important whether we're talking about in C or in assembly is the way we represent numbers, so numeric formats. And 2 that we look at are unsigned and signed. And the reason I keep focusing on this is because when we use various devices, we need to know what are the ranges that we can actually accommodate with those ranges. So it's very important that you be very comfortable being able to quickly assess ranges of numbers and formats. We also looked at representations. And those representations would include decimal, which you've learned, hexadecimal, and of course binary. Now, I don't expect you in your head to be able to go between decimal and hexadecimal, but I do expect you to be able to go between binary and hexadecimal, because we look at SFRs, we look at values of memory, and so we need to be able to go back and forth between binary and hexadecimal. And so these are skills that you necessarily have to have. We looked at a number of various operations at low level, but we're not going to focus on that so much now because we're actually working a higher level language, so we're not so interested right now in terms of how we actually implement those in assembly language instructions. Okay, so then we started looking at the PIC32 microcontroller. And this is where as they say, the rubber meets the road, or the electrons meet the real world. And so now we started looking at how do we communicate with the outside world. First thing we had to do is we had to configure it. So the most important thing that we're interested in right now is clocks. And we know we need to know clock frequencies because when we communicate with the outside world, we need to know how to configure our interfaces for things like baud rate and other important characteristics. So we have two main clocks. We have sys clock, which we use, and this is 80 megahertz. And we have PB clock, and this is 10 megahertz. And we went through all of the details of how we use phase lock loops and so on to be able to, and dividers and multipliers to be able to configure that clock. So that's something that we have to be familiar with because we're going to use those frequencies when we actually start communicating with the outside world. Then we looked at our I/O ports. And so far we've looked at them in a digital for now. And we saw that we have to configure them as inputs or outputs. So we looked at configuration. And we saw that we use SFRs. So recall we have SFRs, and we use SFRs for configuration of the hardware, configuration of the peripherals. We use them for communication with peripherals. We're in that room here. And we also use them to monitor status. So important to know the distinction between SFRs and general purpose registers. When we look at general purpose registers, and I'm just going to abbreviate general purpose registers, we store two things in there. We have data and addresses. And I'm going to put here no instructions. Okay, because sometimes I get this erroneous input that people suggest that we can use in general purpose registers for instructions, which is not true. So when we talk about configuration, we are also interested in open drain for outputs. And now in the I2C, you start to see the significance of using open drain because we have multiple outputs all tied together. And later on, we will look at using I/O ports as analog inputs and also using some of their additional functionality like change notification if time allows. Okay, so when we looked at these I/O ports, we also have to consider, are they all available on the MX7? And so we saw that we have our various I/O ports, and what I want to do is I'm going to, where's my, I don't have it on my taskbar banished. So let's see if I can, there we go. So what I want is I want to come back to, where's my, when I look at the PIC data sheet, and let me see if I can get back to how I was before. Come on. Okay, well, we'll do it this way. Bear with me for a moment. So we look at our I/O ports. We saw that not every port had all pins, and we see that not every port is going to be configured as an analog input as well. So let's return back to our notepad. I don't want to get too sidetracked here because we have other things we want to review. Okay, so we have our I/O ports, and I need to switch out of tablet mode. Okay, and let me do this here. Okay, so sometimes things don't work the way we want. We saw we also have a number of our C library function modes to operate them. The other thing that we saw is we have with our SFRs, we have offsets for clear, invert, and set. So for example, if I looked at the LAT register, which is a register I write to, if I wanted to just adjust one bit, I could, if I wanted to set it to 0, I would use the offset from that LAT SFR, which would be 4, to clear that individual bit, designating that individual bit without affecting the others. Similarly, if I want to set it or invert it, I just use the appropriate offsets to be able to do that using the SFR address. Now we have some C library functions that enable us to do that as well. I need to be careful if I'm using the appropriate function to make sure that I'm using the one that will specifically clear, invert, or set, or if it will clear or set all of them. So if I write to a port, I'm basically writing to all the outputs. If I set an individual bit, then I'm basically specifying the individual bit I wish to set. And so that implementation is going to use the LAT register plus the specific offset to allow me to be able to set it. Okay, so then we looked at timers. And we saw I/O ports, clocks. We looked at timers and we see that we have 5 16-bit timers. And I want to emphasize 16-bit. And we have, I'll do a very quick sketch. We can select from internal or external. We have an enable. We have a prescale. And this goes to the timer register. And this is basically going to, it's a divider that will slow down the clock appropriately. So we have 2 types of timers, type A and type B. We have one type A, which is timer 1, and that has limited divider capabilities. And we have a comparator, and we have our period register. And these compare. So this is a reset, and this is an interrupt flag. And so we can set this period to a specific value, and the timer will count up, and when these two are equal, it will set the flag, and it will also reset the timer, so it will start at 0 on the next clock cycle. So we looked at using these timers, and specifically it's called TXIF. And we can run the timers by monitoring the interrupt flag, or we can use them as an interrupt themselves. So which brings us to interrupts. So when an interrupt occurs, whatever the processor was doing, it basically stops what it's doing. It saves all the information it needs so that it can resume operation after it services the interrupt. It basically goes to an interrupt service routine, does what it needs to do, and then it returns back to what it was doing. And so when we use interrupts, we have 3 requirements. I need a source. Could be a timer, could be a communication port. I need an interrupt service routine. I have to enable the interrupt. And I'm going to say enable the specific interrupt, because we have an interrupt controller that basically is going to process all those signals and feed them to the MIPS processor, and then I need an ISR, an interrupt service routine. And so I can use any number of devices for interrupts, and when I configure it, when I enable the specific interrupt, I have to set the priority as well. I'll just say and set the priority. Okay, so I need to do that to use interrupts. And if I have my highest priority interrupt, then there's going to be a shadow register set that we can use for the level 7 priority. Or there's an internal stack that we can use, and so when I'm doing interrupts, there's a little bit of overhead in that process. And we also have the ability of interrupts to interrupt other interrupts by using the appropriate level of priorities. Okay, so we have 7 levels, and then we have 4 sub-levels for a total of 28 possible levels. Okay, so then we talked about interrupt service routines. And we saw that we have a specific format for doing those. And we also, because we don't know when the interrupts, so ISR is interrupt service routine. And this interrupt service routine is the code that's going to execute when the interrupt occurs. So we want to do something in response to that interrupt. And so what we have to do is we have to write this specific function that is going to be executed when the interrupt occurs. So for example, if the timer generates an interrupt every 64th of a second, I might, when that interrupt occurs, I might want to read sensors, do some sort of processing, and then resume some background task. And so that's, in my experience doing navigation systems, you have to periodically read accelerometers and gyros, and so you have you call it a heartbeat. Every time this heartbeat, the interrupt goes off, it's basically a signal to start reading the sensors, doing your navigation calculations for that particular iteration. And so you would do that so many times a second so you can maintain accurate position and attitude information calculations. Okay, so then for our ISRs, because we don't know when they're going to occur, so there are no arguments passed to an ISR. Similarly, an ISR can't be called by any other function. And I'm going to say cannot be called directly. So you can't have your main program call this ISR, call its function name. And because we don't know when it's going to occur, an ISR cannot return any values. Now, an ISR can set flags, global variables, and so that's a good way that you could use to be able to signal that, okay, it's time to do something, signal the main program, and have it do something in response. And I'm going to put this last one. This is a suggestion. Ideally, now that brings up an interesting topic. Is recall in the peripheral library, we saw that we have a whole bunch of functions that we use to do various things with peripherals. And some of those are also, they have an M prefix indicating they are macro instructions. And others that maybe are not explicitly indicating that they're macro instructions are basically macro instructions as well. What that means is rather than calling a function, and recall when you actually did get a chance to do labs, you would call functions and you had to make room on the stack to pass arguments, to save registers, and so on. Well, a macro instruction simply inserts code related to that operation that's done by the function in the program that is calling the function. So if I look at my disassembled code, if I had a macro instruction that would talk to a port, basically what I have is I have an instruction that's basically moving data to that SFR location. And so it's basically substituting the equivalent code for the function call. So let's see, question is, an ISR cannot return any values. So this is a U. And that's the nice thing about this is I can do that. Okay? All right, so we have those constraints for our interrupt service routines. And recall, important, I'm going to an ISR must clear the interrupt flag. Okay, so why must an interrupt service routine clear the interrupt flag? I'm posing that question. Why must the interrupt service routine clear the interrupt flag? Any volunteers? There's 41 of you out there. One of you should be able to volunteer. Okay, well, the comment is because nothing else will. So if the interrupt service routine does not clear the interrupt flag, you will have one and only one interrupt. It will stay in that state until it's cleared, so you will have no further interrupts. So let's say I'm writing code for a navigation system and I forget to clear the interrupt flag. I will read the sensors only once, and I will never ever read the sensors again because I have no trigger to actually go back and read the sensors. So when you're writing your code, it is important that first you clear the interrupt flag before, well, when you first interrupt or first initialize your device, you want to clear the flag just as good programming practice, and you want to, in your interrupt service routine, clear it as well. Otherwise, you won't get any subsequent interrupts after the first interrupt. So then we talked about communication. And I'm going to say serial communication to be specific. Okay, so when we talk about serial, one important characteristic is it transmits 1 bit at a time. That's the bad news. But the good news is today we have serial communication links that are considerably faster than they ever were years back, and so we see a lot of trends towards serial interfaces for things like disks and other devices as well. We have two characteristics. One is whether it is synchronous versus asynchronous. If it is synchronous, then I have one of the devices, the master, transmitting a clock. If it is asynchronous, then I have my two devices that are communicating, or all devices that are communicating. They're going to extract their synchronization from the signal itself. But they're not going to just do it. There has to be some knowledge of the characteristics of the signal to be able to do that. Then we also talk about full duplex versus half duplex. And this is, I'm going to abbreviate, transmit and receive simultaneously. And we have one transmit at a time. Now, we have different configurations. We have point-to-point, or we have bus-oriented communication. So some of the devices we look at, or some of the configurations we look at, are point-to-point, and some are bus-oriented. So point-to-point and bus-oriented. And one of the things that I will mention is every single one of our interfaces that we've talked about, our serial interfaces, including the UART, the SPI, and the I2C, are all capable of operating in bus-oriented configurations. However, we also look at, well, let's talk about the UART. With the UART, we are specifically looking at a format that we use, which is point-to-point, which is RS-232. But it is also capable of a bus-oriented with RS-485, but we'll focus on RS-232. So with our UARTs, these are full duplex, and they are asynchronous in the mode that we use. And this is using RS-232. And RS-232 is not the UART itself. It's a protocol that we use in concert with the UART to be able to send full duplex asynchronous point-to-point. So this implements point-to-point connections. And it's kind of good news, bad news. The good news is some of these devices have a multitude of modes that we can operate them in. The bad news is it makes the configuration a little bit more complex, because if we want to use all of these different modes, the configuration gets to be a little bit more complicated. But we saw in the UART, it has some interesting characteristics in that we are going to extract the signal directly, or extract our timing directly from the signal. So in my steady state, and I'm looking at the UART output, not the RS-232, so I'm looking at the logical level, I see that I have my steady state is at a logical 1. I have 1 bit time, and this is my start bit. And I'm going to do it this way. So I have 1, 2, 3, 4, 5. Getting a little sloppy here, sorry. So I have 8 or 9 data bits. Now I could have 8 data bits. I could have, and I'm going to do this several different ways. I could have a 9th data bit, and I need to do my erase. Okay. And so if I have 9 data bits, my last bit is going to be a stop bit. So this is stop. This could also be or parity. This 9th data bit could also be a parity bit. And if I only use 8 data bits, then I'm going to, so here's my 8. Then I'm going to have my last bit, this be a stop bit, this entire bit time, and I might have 2 stop bits. Optional second stop bit. And same thing, this, I could have a second op. So if my 8th data bit is 0, I'm going to have a 0 to 1 transition for my stop bit. If it's a logical 1, I'm going to have another complete bit time. So one of the things, when we configure it, we have to talk about baud rate. And this is basically the bit time, the duration of 1 bit. Then we talk about the number of data bits. And this would be 8 or 9. We have parity, and I'm going to say with 8 bits. And this could be either odd, even, or none. And then we have the number of stop bits. And this is 1 or 2. So you will see things like 8 and 1, which means 8 data bits, no parity, and 1 stop bit. So this is data, parity, and stop. So this is a standard notation that you will see with UARTs. So key thing is when we use our UARTs, we have to be in agreement, both sender and receiver having exactly the same format. And we looked at the configuration. We can generate interrupts when we have a number of interrupt modes that we can use for transmit, receive, errors. And so if we want to use, we have to decide how we want to configure that. We also looked at data encoding. And we are all familiar with ASCII. Here we use 7 bits, and the 8th bit is equal to 0. And we saw that we cannot represent every character that computer users want to use today, so we have a different encoding scheme called UTF. Well, we have Unicode, so Unicode, and I'll call this a listing of all characters. And they're given a reference called a code point. And the way we can encode this listing of characters is with an encoding scheme called UTF-8. And this is an encoding scheme. And what UTF-8 does is it says, I'm going to encode characters, and if I have bytes that have the most significant bit equal to 0, then I know those are just plain Jane ASCII characters. If I have bytes that have the most significant bit set equal to 1, then I know that this is going to be part of a sequence of bits that are used to encode characters. And so I have to decode those accordingly. Okay, so then we looked at SPI, and we saw that SPI is a different kind of interface. So let me make sure here's my UART, here's my SPI. This is a synchronous full duplex communication link. It's serial. And my UART is also serial. And so we saw that we can configure this, and I basically need at least 3 signals. And I'll just do a little sketch. So again, this is so I have my clock. I have SDO. This is SDI. And here's my SDO. And that's connected to this guy here. Now, when I want to communicate with, so I'm just going to say here's slave 1, here's S2. Now what I need is I need a SS, and here's SS. So now I need 2 additional lines to be able to select which slave device. So here's my master, and I have 2 slaves. So now I need additional slave select lines. So these are and so because of that, when I use an electrical slave select, now my implementation electrically is going to be a little more complicated, but my communication protocol is very straightforward. We saw when we looked at the signals, they were very, very straightforward, and my implementation now requires more and more I/O port lines to allow me to be able to do this slave select. Whereas I2C or I2C, this is synchronous, and this is half duplex. And it is serial. And as you saw in the beginning of our discussion today, the interconnect is very simple. In fact, this is often called 2-wire because that's all we need. But I'm hoping that after this earlier discussion, you see that the communication protocol is considerably more complex, because now we have to transmit addresses, We have all this acknowledgement that's done in the signal, and part of the challenge is now I have all of these signals asserting signals on the line intermittently. They're intermingling who is basically asserting a signal on the line in very, very close proximity in terms of time. And so we see that the SPI and its implementation is considerably simpler for the protocol, but it comes at the expense of having to have more interconnects. And so we've looked at a number of the interfaces on the PIC microcontroller, and in the labs I'm hoping you're starting to, if you're looking at the videos, which you should be, then you're starting to see the versatility of this single integrated circuit that we use for a lot of these embedded applications. And we're not even close to done yet. We'll start to see more after we have our next test. So the next test will be on Tuesday. I'm going to make it available first thing in the morning, and you will have to turn it in by Friday at noon. So you have plenty of time to work on it. There's no time restrictions. And I'm also going to give you 2 attempts. So if you're not quite sure and you want to go back and make sure you understand the question and the answer, I'm giving you that opportunity to do it. My motivation is not so much that I want to have a spread of scores. My motivation is I want you to learn the material. And so if you can go back and feel confident that you can answer those questions, then I think that we've accomplished the mission. So any questions regarding the plan for next Tuesday? We will have a lecture on Thursday, and we're now going to start moving into the realm of dealing with the real world and analog signals. And we'll start looking at how we deal with analog signals, signals that you and I sense, we hear, we see, and so on. So now we need to start processing those so that we can actually deal with them in a digital realm. And this makes life more interesting. So any other questions, and I will stop the recording here. Okay, so let's see. There was a question here on interrupts. So there will be no lecture on Tuesday. And the question, let's see if I can. So, question on interrupts. So the exam is not timed. And I'm sure there's a question on interrupts. So there are three main classes of interrupts distinguished by use case and ISR. So the interrupts are basically, you can set up interrupts for data being available, data being available to read. You may have a buffer that is empty that you want to continuously transmit data, or there may be error conditions to which you wish to respond. So you can set up any one of them or all of them as appropriate for your application. You have a lot of flexibility in terms of those interrupts.
Hey, Dr. Nava.
Yes.
How much of the clock manipulation, when we talk about scaling the clock and pre-scaling, how much of that is kind of an artifact of the MX7 board, and how much of that did you have to do in your previous life when you were at Sandia?
So with the I2C, that is more a characteristic of the protocol, of the microcontroller and the peripheral device. And so because they have to adhere to that acknowledgement protocol, the I2C is a little bit more complicated when you're tying those devices together. Other devices tend to use things like individual hardware handshakes. So many devices will make the trade-off of using actual electrical connections so that they can simplify the interface and the timing protocol. So my experience has been most hardware tends to use discrete signals so that you can signal acknowledgement and negative acknowledgement rather than embedding it all in the protocol. It makes life simpler. Any other questions? Okay, well, I'm going to stop the recording.